All right, so let's look at our first example of a hypothesis test. It is hoped that a newly developed pain reliever will more quickly produce perceptible reduction in pain to patients after minor surgery than a standard pain reliever. The standard pain reliever is known to bring relief in an average of 3.5 minutes with standard deviation 2.1 minutes. To test whether the new pain reliever works more quickly than the standard one, 50 patients with minor surgeries were given the new pain reliever, and their times to relief were recorded. The experiment yielded a sample mean of 3.1 minutes and a sample standard deviation of 1.5 minutes. We want to know, is there sufficient evidence in the sample to indicate at the 5% level of significance that the newly developed pain reliever does deliver perceptible relief more quickly? All right, now let's go through our steps. First thing we've got to do in any hypothesis test is identify the null hypothesis and the alternate hypothesis. The null hypothesis is always kind of what's already accepted. So let's notice that the standard pain reliever relieves an average of 3.5 minutes. So that's what's already been going on traditionally for a long time. All right, so let's write our null, and let me just clear this screen for you. So our null, h sub 0, and I'm just going to write it as h0, and I'm going to write mu instead of finding the symbol, all right? But our population mean, in this case, is going to be, what was the time? Oops. 3.5 minutes. All right, so mu is 3.5 minutes. Now, you'll notice that pretty much every time that we're looking at examples, our null hypothesis will always be of the form either mu or p equals something. All right, so always equal, whereas our alternate is going to reflect that it might be left-tailed, right-tailed, or two-tailed. All right, so let's take a look back at our example for a minute. Okay, so we want to know if the new pain reliever delivers relief more quickly. Now let's realize that if it delivers relief more quickly, that really means that it's taking less than 3.5 minutes to work. All right, so despite the fact that we have the words more in there, we're really looking at less time to be more quickly. All right, so let's go back here. Since we want it to be less time, we want for the mean to be less than the 3.5 we had in the null. And our alternate hypothesis will always be one of three types. It could have been mu is less than 3.5, it could have been mu is greater than 3.5, or it could have been mu is not equal to 3.5. In this case, of course, it ended up being less than 3.5 from our wording. Okay, now let's also identify while we're here what alpha is. All right, so if we look back, we want a 5% level of significance. The level of significance is alpha. All right, so we want 5% or 0.05 for alpha, always as a decimal. All right, the next thing we're going to do is establish what our critical value is. All right, since it's a left-tailed test, we only have to find out what the z-value is on the left side. And recall, whenever we look something up in Excel, we're always looking up the area to the left. All right, so in this instance, all we've got to do, since it is a left-tailed test, is go equal norm.s inv, oops, and put in our 0.05. And that gives us negative 1.645, we'll call it. Okay, so okay, now just for a moment, let's kind of draw a picture of this. So here's a picture of our standard normal bell curve. I know it's not very pretty given my drawing ability on the computer, but remember that on the standard normal bell curve, 0 is right here in the center, and so the negative 1.645 that we got from Excel is over here. We're looking at a left-tailed test, which means that anything that falls over in this left shaded region right here, we will count as being in our rejection region, and we will reject the null hypothesis. Our negative 1.645 is called our critical value, and so anything to the left of that critical value rejects the null hypothesis. So let's go back to our situation. We got our critical value, and I'm going to kind of label it here, because you're going to have questions that ask you for that critical value. Now we need to get our test statistic. Now, to get our test statistic, we have a different computation, but it's a computation that we've seen before. So there's our formula. We've seen this z-score before, but this is, we're going to compute the test statistic with this formula. And test statistics always are formulas that we have to plug into, whereas critical values, we're always going to use our Excel command to get critical values. All right, so let's get our test statistic. Let's go back to the example for a moment. And if we look at our sample, X bar was 3.1 and the standard deviation was 1.5. So we're going to have 3.1, and our mu is up here in the null hypothesis. It's 3.5. And let's see, our standard deviation, if we go back, was 1.5. Sorry, my dog's making a lot of noise in the background. 1.5. And we want to divide by the square root of our sample size, which if we look back, our sample size, there were 50 patients recorded in this sample. So we want to divide by the square root of 50. All right, so let's stick that into our calculator and see what we get. On the top, we're going to get negative 0.4. On the bottom, we're going to get 0.212132. And then I will do that division. We're going to get negative 1.89. Okay, now let's go back to our critical value. We said, when I showed you that picture, that anything in the rejection region, anything to the left of this negative 1.645, we would reject the null. And negative 1.89 is definitely in this region. It's to the left on the number line of negative 1.645. So it's in the rejection region. So next thing we want to do is we want to write it's in the rejection region, which means we reject the null hypothesis. All right, so by rejecting this null hypothesis, we're embracing the alternate, that the mean is less than 3.5. And we always want to make a final statement about what all of this means. So there is significant, if I can't spell, significant evidence, and we state our alpha value, alpha is 0.05, to reject the null hypothesis. Evidence suggests that the mean is less than 3.5. it appears that the new drugs do work more quickly than the old drug. Okay, so notice that we've said whether we reject, or if we don't reject the null, we say fail to reject. We never say that we accept the null, because generally a scientist wants to disprove the null hypothesis. So they're just saying, oh, I don't have enough evidence at this time. So we say fail to reject if we are not rejecting it. And then we say evidence suggests that the mean still appears to be 3.5 or something like that. But notice in this case, we said that it is less than 3.5. We are saying that our alternate that we had right up here is true. And then we want to apply it to the situation at hand. And here it means if that alternate is true, it means the new drugs are working more quickly than the old drugs are, which is an important conclusion.